things we were talking about, we didn't prove them last time. So this is kind of an interesting thing that tells you something about transcendentals, right? So if you have a field and a transcendental element, the smallest field that contains K and U is essentially the same thing as rational functions over, over K. And this phi that we have here, you can construct a phi that's fixed on, the identity of K. So proof. Yeah. Now remember what this is. This is rational functions, right? And this is the set of f of u over g of u, where f and g are in kx. This is the notation that we introduced last time. We pointed out this is, of course, field, right? Well, this is the notation here. We're going to take phi. What's a typical element of rational functions? Well, it's like this. And this is going to be f of u. I'm kind of gonna, I mean, technically, if I really wanted to go all the way down the road here, I have to worry about well defining this. But of course, one of the things that I could do is I could assume that this is in a reduced form, right? Because Kx is a PID, so it's UFD. But anyway, this is how you evaluate rational functions, right? So phi is a homomorphism. Well, first thing I really need to do is claim I am. I claim the phi is well defined. Now, the first thing that I have to worry about is that numerator, right? Or I'm sorry, the denominator. That if p of u is equal to 0, that's certainly a problem we would have to face. Then what can we conclude? The g of x is identical to 0. It must be the 0 polynomial since u is transcendental. Okay. That's the important piece right there. Right. So now suppose, be really careful. Then note that that certainly must be the case. Therefore, f1 of u, g2 of u equals f2 of u, u1 of u. because these are all polynomials, right? And therefore, F1 of U over G1 of U is equal to F2 of U equal to G2 of U as U1U, G2U are not equal to 0. So this function is well defined. It's fairly easy to see this is a homomorphism. Because I mean, this is really the way that we evaluate rational functions, which is the same way we evaluate polynomials essentially. Clearly phi is onto, and I hate using the word clearly, it makes it really sounds obnoxious. But the reason it is clear is because this is the very definition of KU, right? So that's why it's onto. What about one-to-one? Well, first note, so I'm going to do this. First note that phi restricted to K is equal to the identity on K. Everybody agree with that? If you have like just an element of K over 1, then plug in U and it's just K. Everybody agree that it's the identity restricted to the base field K? Looks like I kind of had a little mini stroke there. I just started talking about something other than one-to-one, but this is actually helpful. So in particular, phi is not the 0. Everybody agree with that? Now notice that K of X is a field, right? And the kernel of phi is an ideal of X. Right? Now, so the kernel of phi is equal to 0 or all of Kx, because it has to be an ideal. But phi is not 0, so kernel of phi is not equal to Kx. Therefore, kernel of phi equals 0 and phi is 1. And there you have it. So that's an isomorphism. And that's I did that proof because I think that's an important thing to remember. We're going to do a lot of mapping between fields. When you have a homomorphism from one field to another, you've got two options. It's either the 0 map or it has to be one-to-one. The kernel of any maps that begins with field, and especially if I demand that the identity of the ring goes to the identity of the ring, then the kernel can't be all of the field. So if I have a homomorphism from a field, actually doesn't matter where it goes, the field's somewhere else, it's got to be one-to-one. Okay, any questions? Okay, so now here's the fun stuff. Let's start to deal with the weight algebraic extensions. Okay. Like K inside F, fields will let U and F be algebraic over K. Then, number one, remember the distinction here, this is the smallest ring that contains K and U. So basically, this is all polynomials in U, kind of abusing the terminology. This is the smallest field containing K and U. So this is all rational functions that you can build with U, as long as your denominator is not zero. Number two, KU is Kx modulo the ideal generated by f of x, where f of x is the minimal, or this way, irreducible polynomial. For U over Kx. So I did say that U and F was algebraic. That means that there's some polynomial f of x for which U is a root. Among all such, pick one of the smallest degree. 3, the degree of KU over K is equal to the degree of this f of x in AX. We don't call it in. And number 4, every element of K of U can be written uniquely in form sum KI UI I equals 0 to n minus 1 with n equal the degree of KU over K. Okay. So here's some important stuff about an algebraic element U. The smallest ring that contains K and U is actually a field. That's nice. And in fact, it's always in this form. It's the polynomial ring over K modulo this polynomial that's the minimal polynomial for U. The degree of the extension of fields here is n, which coincides with the degree of this polynomial. And every element in KU can be written uniquely in this form. So let's prove this one by one. Well, I mean, that's always true, isn't it? And so we only need to show the other containment. Let's show equality. It suffices. I don't need KX. I mean, and that's another ism. KU suffices to show KU is all right, so how are we going to do this? I'm sort of going to prove part two along the way, or at least mostly. So I want to show that KU actually is a field. Certainly this one's a field, and so if this one's a field, you must have equality, because this is the smallest field that contains both K. Everybody okay with that? So, let X in KX such that G of U is equal to 0. So what I want to do first is I want to look at this ideal in KX, right? And what I'm going to do is I'm going to collect all the polynomials in KX as G of U is 0. Now I know one polynomial for which is true. This is the 0 polynomial, right? However, I has to be more than this because U is algebraic, right? So there's at least one non-zero polynomial in this instance, 0. Okay, and so what do we know about the structure of K of X? It's principal ideal domain. There exists f of x, not 0, in I, such that I f of x. See, say this statement here later. Note that, so let me just note, for all G of x and K of x, such that G of U equals 0, f of x divides it. Right? That's, you gotta love that principal ideal thing, right? F of U is 0 and it divides every other polynomial. So it's minimal, right? It's gotta be the smallest degree. Yes.
We already said that this f of x is the same as the minimal polynomial of u.
Yes, that's right. And that's what, this is what gives us that f of x is a minimal polynomial, is it generates the side. Am I okay with it? Okay, so what do I want to do now? Consider the function phi in kx and k squared bracket given by the easy thing. So take any polynomial, just plug in u, that's my function. Right. This certainly ends up in KU, right? I agree with that. This is clearly onto, again, by the definition of what KU is, this is clearly onto, right? Don't expect it to be one-to-one. The kernel of phi is equal to the set of G of x such that G of U 0, which is precisely I, which is x. Note fx is irreducible. Can be reduced because h times k of x and u is a root of h or k. Right, because if f reduces, then that means 0 is h of u times k of u, making u a root of one of these, right? But f of x had the smallest degree for which u is a root. Everybody okay with that? So f of x is irreducible. And so what does that make it? Well,
Kx or I is of u.
this means that f of x, as f is irreducible, f of x is a prime ideal. And what do you know about a non-zero prime ideal with principal ideal domain?
Maximal.
It has to be maximal. Notice that Ku is isomorphic to Kx mod kernel of phi. Kx mod the ideal generated by Fx. But this is a maximal ideal, and so what can you say about this? And then with this, well, let me see what we did establish. Well, how about that? This establishes 1 and 2. Right? Got the equality of these two, and we see that Ku is this, where f of x is a polynomial. Right? Everybody okay? The last 2, 3, and 4 kind of go hand in hand as well. Yes,
What were we doing there at the end?
right here.
Yeah.
I'm trying to establish that f of x is actually an irreducible polynomial in Kx.
Is that how it's together? Exactly.
Well, if it reduces like this, where both of these have to agree at least 1, since u is a root of f of x, that means that h of u, k of u has to be 0, right? Which means the product, these are two elements of the field. If their product is 0, one of these has to be 0. That means that u is a root of either h of x or k of x. And that's a contradiction because f of x is the generator of this.
Okay.
Right. Okay. Other questions? Okay. How about the next bit? Well, so let f of x be minimal polynomial. Well, let me be dramatic and write this out. 0 plus a1x plus a n x n and k of x the minimal polynomial for u, and we can assume a n is not 0 because otherwise it would just be one lower degree. By the way, just for chuckles, I can probably also assume a 0 is not 0. Why is that? I can also assume that this is not 0. I'm not going to need it, but I could assume that. Okay. Because then it wouldn't be irreducible anymore, right? So. Okay. So I'm gonna make the following claim. The set of elements, one u squared, all the way up to u to the n minus one, is a basis for ku as, well, and I'll write this parenthesis, as a vector space. Over K. So I claim that that collection of powers of u gives me a basis for my vector space. Ku over. Okay, so note, well, what's it now?
They're not independent because we know we don't have to degree.
Right. So let's first do that. Suppose K0 plus K1x plus Kn minus 1 un minus 1 is equal to 0. All right. Didn't write x here, I'm going to write. This means so u is a root of but our minimal polynomial f of x was of degree n, right? So k of x, the only way I can still be in that ideal is to be the zero polynomial. That is to say, K0 equals K1 equal Kn minus 1. And this set is linearly independent. Okay. The next thing I need to do is show that it spans, right? So how do I do that? Yeah.
I guess I can divide every polynomial by f of x and express it like f of x times 2x plus rx, where r will have degree less than f, and well, then evaluates in u.
You can do induction on the degrees, but I like that way better. That's it. I think that's even better way. So suppose we have some arbitrary suppose we have some arbitrary element here. A0 plus A1, right? K0 plus K1U plus KM UM. It is convenient that I can use that polynomial instead of having to use rational function notation, right? I can visualize this as is equal to, G of U with G of X So I can visualize this element of KU as just taking this polynomial KX and plugging in, right? Well, I'm gonna manipulate that polynomial a little bit. So see, you thought you may never use this again, but in fact, not only is KX PID, it's Euclidean domain. And so we can divide, we can take this G of X I've got over here and divide by F of X. So my G of X is equal to, let's say, Q of X times F of X plus R of X. Where, whoops, Q of X and R of X are in KX. And what do we know about R of X? Right, it is either zero or degree of R of X strictly less than N, the degree of F of X. Right? Notice now that G of U, which was our element, is equal to Q of U, F of U, plus R. But of course, U is a root of F, so this is gone. That is, G of U is equal to K0, K1U plus KM UM is equal to this thing here, which is, let's say, R0 plus R1U plus R n minus 1, U n minus 1. Because either all the coefficients are 0, which is okay too, or this has degree n minus 1 class. And so an arbitrary element here is actually spanned by this. Therefore, statement 3, degree, or I'm sorry, KU, okay, equals 3F. So N. And statement 4 follows immediately, right? Because we've already proved that the powers of U from 0 to n minus 1 form a basis. And so it's well known that you get a unique representation. Okay, any questions on that?
So this Euclidean algorithm on the KX guarantees that Rx is unique, right? So really 4 would follow immediately without having to do that. The argument with the dimension. So we kill two birds with one stone.
Yeah, that's right. That's right. All right, other questions, comments? Okay, Here's an interesting example that's a spin off of this. I find this a little bit kind of interesting. So here's an example.
Yeah, I know, I'm saying.
Okay, if you look at this polynomial here, this polynomial is an increasing polynomial. And of odd degree. So it has to have a real root. And the fact that it's increasing means you've only got one of them. And if you think about it, what are the roots of this? Well, you've got the real cube or the fifth root of 2. And then you've got 2 pairs of complex conjugate roots. Well, if we look, for example, at Q adjoined with U, what should the degree of this extension be? Okay. Okay, answer my question. This polynomial is factor reducible by Eisenstein criteria for the prime 2, right? Everybody okay with that? Now, by the theorem that we just did, so that I think this is kind of an interesting consequence of it. QU, this field we've got here, is isomorphic to QX modulo this polynomial. If I agree with that. But this should be true. How many roots are there in this? There's 5 of them. And in this construction, Q of X can't tell which root you're adjoining, right? I mean, there's 5 roots of this, and it doesn't matter, right? You can't tell apart. This is isomorphic to QZ, where Z is a non-real root. So,
Why is that again?
this is isomorphic to Q root of 5, or fifth root of 2, that is, where is a primitive fifth root of 1. And so if you like in these computations, like I, 2 pi, and you can actually express this in terms of sines and cosines and so on. Right? Notice these 2 fields are isomorphic. This one is a subfield of the real numbers, and this one is not. And the reason is these 2, to answer your question, these 2 things are roots of the same minimal polynomial. Right? So this thing right here, isomorphic to QX mod minimal polynomial, same as this. That's kind of strange because these 2 fields are isomorphic. One of them sits inside the real number, so it's a real field. And the other one has all kinds of, gobbledygook that's not real floating around in there, right? Which is kind of, maybe it's a little bit surprising, but we'll see. Lots of cool examples like this. Okay, any questions? Yes,
Why is the minimal polynomial unified?
well, certainly this is a root of this, right? So the minimal polynomial has to divide this. But this polynomial is irreducible by Eisenstein's criterion.
Okay.
Everybody, okay then. Okay. Theorem. 8, 9, 9. But suppose we have, what an isomorphism of fields. And U and an extension field of K. And B and an extension field of L. Then we can extend this original isomorphism, then this original isomorphism, I can extend it to an isomorphism, uh, taking U to V, let's extend it, let's call it a hat on it. If and only if one of the following holds. You want to guess what the conditions are? What's that?
Both are transcendental.
Okay, one. U is transcendental. Over K. And B is transcendental. Over L. Or what do you, how do you suppose we handle the algebraic?
Same minimal.
Essentially,
But if you say that the minimum polynomial has the same degree, both do, right?
I should say minimal, let's say. Yeah. B is a root of minimal. And let me make clear what I mean. I'm being a little bit sloppy because, why am I being sloppy? Because this only acts on K, right? So what do I mean by polynomial? I mean, what I do here is I just look at the coefficients and see what they do to separate coefficients. This thing leaves X alone and just takes the coefficients where they need to go. So, in both cases, so before I even differentiate, this can be extended to you can extend this here where X over G of X equals clear for once. So you can always extend this, whether or not any of these guys are algebraic, you can always extend this transcendental thing here. Then in the first case, we have, compose these maps to get what I call P with a hat on it over here. And notice that U goes to X by our previous theorem, X goes to X, and then X goes to V. So U goes to V, and these things all fix the base field. Well, these all act like the homomorphism. This first one fixes the base field K. This does a little tornado to it, and this one fixes the base field L. In the other case, if it's algebraic, then just look at the composite homomorphism. KU isomorphic to L. And it's the same old thing. So let me point out, I think this is kind of a good point to make here, before we call it a day. Note. So this is an explicit statement of what we did in this example before. If f of x is irreducible over k, and u, v are roots of F(x) in some gargantuan extension field, then K of U is isomorphic to K. That's an important thing to keep in mind. Okay, any questions? Yes.
How does isomorphism in the middle work?
Oh, that's induced by the one that just took X to X, right? So what it does is, what this one's doing is it takes X to X and it takes the elements of K to the elements of L using this thing right here. Right? Because remember, that little tornado thing took elements of K isomorphically to L. So you're taking the elements of K isomorphically to L, and you're taking X to X. So see if you can figure that one out. Okay, others. Yeah.
That is true in general. If A is isomorphic to B and C to D, A over C is isomorphic to B over D.
Oh, so. That, no, that's not be true. Yeah, that won't be true in general. Yeah, so for example.
Oh, yeah, C and C.
All you need is like an infinite number of copies of Z. And another infinite number of copies of Z, it just,
You can take C,
Just-
A and B equal to
Right.
C and C, to Z,
right,
and C equal to 2C, I don't know, and three, and D equal to 3C.
so if you have A and B, this. What you can do is mod out by. You can kind of shift them over. These two are isomorphic and these two are isomorphic, right? But the quotient here is one copy of Z and the quotient here is two copies of Z. So, yeah, you don't expect this to happen, but so check it. This does happen in this case. Notice that my counterexample is very large, right?
Yeah, I was thinking you can take A and B equal to C, and C equal to 2C, and D equal to 3C, and.
Yeah, right. Okay, other questions? All right, well, I will see you all on Wednesday.